Alright, in this video we will be looking at areas under a curve, and in particular we will be finding the area between this function and the x-axis on the interval 2 to 6. So the first thing I like to do is set up a summation. So this is the summation that my students use. Where delta x represents the width of each rectangle that we are trying to find. And you can find that delta x is just b minus a all over n, the number of rectangles. So in this case it'd be 4 over n, and a and b are just right here. There's a, there's b. So a here would be 2. And we're looking for delta x and a because that is what is in the formula here that we need. I is just I. We do not substitute anything in for I. So the next iteration of this summation looks like this. We will have the sum as I goes from 1 to n of f of, let's see, a is 2 plus 4 over ni, all of this times 4 over n. The next step here is I want to figure out what this function value is. This is how we find the height of each rectangle, and this is how we find the width of each rectangle. So we mentioned that earlier. Delta x is the width for each rectangle, but this gives us the height. And if we can multiply height times a width, we can get the area of a rectangle. And then what we do is we add up a bunch of rectangles, the areas of a bunch of rectangles, and we can find the area underneath the curve. So f of 2 plus 4 over ni is the same thing as 25 minus 2 plus 4 over ni squared. And you can see that by the substitution here. F of whatever is 25 minus that whatever being squared. Check. Then we're just tasked with actually squaring that binomial. So you'll get 25 minus 2 squared is 4. You'll have 2 times this term times 2. So 4 times that term would be plus 16 over ni plus 4 over n times I, the quantity squared, is 16 over n squared I squared. And if we combine some terms together here, we're left with 21 minus 16 over ni minus 16 over n squared I squared. And so this whole piece here gets replaced with 21 minus 16 over ni minus 16 over n squared I squared times 4 over n, the summation as I goes from 1 to n. So we have this information here. The last piece that we need to do with the summation anyway is make sure we simplify the sum. So in order to simplify the sum, we take this delta x that we had originally here, we just need to distribute here, here, and here, and then start simplifying the sum. So the sum as I goes from 1 to n of 84 over n minus 64 over n squared I minus 64 over n cubed I squared. Now we can split these terms apart and say that the sum as I goes from 1 to n of 84 over n minus the sum as I goes from 1 to n of 64 over n squared of I minus the sum as I goes from 1 to n of 64 over n cubed I squared. And I'm going to continue this on the next slide. And so here you can see that I just have the last step on the last slide. The next thing that needs to happen in order to figure out what all of these sums are is that we need to take out any constants. Now this includes any number and any n's that you see. N is just a number. So we are allowed to take this 84 over n and this 64 over n squared and this 64 over n cubed and take it right outside of the sum, out to the front. So it'll look something like this. Here you go. You can see that these constants have been factored out of the summations. The last thing we need to do here is actually find these summations. And you need to remember these formulas in order to successfully sum 1i and I squared. So with these formulas off to the right, this expression becomes 84 over n times n minus 64 over n squared times n plus 1 over 2 minus 64 over n cubed times n plus 1 times 2n plus 1 all over 6. So here we have this summation becoming n, this summation becoming n times n plus 1 over 2, and this summation becoming n times n plus 1 times 2n plus 1 over 6. Now would be a good idea to do just a little bit of simplification, like the n's cancel here, one n cancels here, one n leaves us with a square, cancels here. And we can do some distributing and foiling in these terms if necessary. And that leaves us with something like this. When you FOIL this out and distribute the 64, you'll get this. 6n squared in the denominator. 64 times n plus 1 is 64n plus 64. 2n in the denominator. And then the very last step, this is about as simplified of a summation as you can get. And the idea here again is you can pick any number of rectangles. That's what n represents. N represents some number of rectangles. And the more rectangles we use in our calculation, the more accurate the true area is represented. So the idea is we want to use as many rectangles as we possibly can. And so step 4, the very last one, we want to take the limit as n goes to infinity. You can't get any better than infinity. And we want to find the limit of that whole expression. Well, since we have the same degree in the top and the bottom here of this fraction, we can just take the ratio of the leading coefficients. So we would have 84 minus 64 over 2. And the same thing that happens over here with this fraction. We have the same degree top and bottom, so we can just assume as n goes to infinity that this fraction or this rational expression, has a limit of 128 over 6. Minus 128 over 6. So now we have some numbers that we can easily compute. So let's do that really quick. 84 minus 64 over 2. That becomes 84 minus 32. And then 128 divided by 6 is 21 and 1/3. I'm going to write it like this just so I can do some pretty easy subtractions here. So I have 84 minus 32 is 52. Minus 21. 52 minus 21 is 31. Minus 1/3 is 30 and 2/3, or if you like, 92 thirds. So this would be the exact or the true area for the function given. I believe it was 25 minus x squared equals f of x on the interval 2 to 6.